Hello everybody, this is the third video for chapter 4 of the statistical learning class. So at the end of the last video, we've introduced piecewise constant predictive functions. So the rationale why we introduced this is that earlier in this chapter, or even in chapter 3, a lot of methods we've introduced had a global behavior. So the parameters, whenever, let's say in linear regression, we switch the value of one parameter, then the predictions change for every possible value associated with this predictor. So we then introduced a new approach which was deemed local, where when you switch one of the parameters in the prediction model, so one of the beta, the predictions shift for a certain amount of values for the associated predictor, but not for other values. And we're going to see that a lot of prediction models are based on this idea of more local behavior of parameters rather than global behavior. Okay, so we had, for instance, let's go back a few slides. So we introduced the following predictors. So let's say we had initially a single predictor in our database, X, then we can deduce, we could define new predictors as C0, which is 1 if the predictor falls below some value, real number C1, capital C1 of X, which is again an indicator if the variable falls between a constant C1 and a constant C2, and etc. And we saw that for these predictors, we obtain a predictive function like this. Okay, so we have something like this, where this is B0, the height of this bar is B0, the height of this bar is B1, and etc. We continue like this. So for in our model, if we change the value of B1, only the prediction, so this is Y hat, this is X. So if you change the value of B1, for instance, you only change your predictions for a few values of X, but not for all values. Now, clearly, there are drawbacks associated with prediction functions of this form. The first drawback is that this function is discontinuous. So add the knots. So let's say this is the knot C1 here. This is the knot C2, etc. So at the knots, there are jumps in the predictive function which might not be very natural. So many phenomena, you expect them to like vary smoothly, or like at least the expected value of the target, you expect it to vary smoothly in terms of predictors. So having these kind of jumps or discontinuities is not very reasonable for many applications. Also, the fact that you have piecewise constant values, so maybe instead of having steps like this, you expect to have a more smooth variation within the buckets, or like within the intervals C1 or C2 to C2, C2 to C3, etc. So instead of having something constant, maybe you'd like to have a decreasing function in the above example. So this calls for an extension of the existing method to provide cleaner behavior for prediction. So the first approach that is proposed here is to relax the assumption of being constant over the subintervals. So we can, instead of having constant functions, so a constant function is a polynomial of degree 0. Well, we can change that and assume that over each subinterval, so between the various knots, the predictive function is a polynomial instead of being a constant function. Okay, so we change the degree 0 function to a degree, let's say, small d polynomial. Okay, so if we have that, if we want that, we can set up these kind of predictive functions through the following linear model. So we can assume that the target is, once again, the noise term plus this, where here this summation entails summing over all the subintervals within the predictive function. And for each subinterval j, you will sum d plus 1 terms here, where each of these d plus 1 terms correspond to one monomial in the polynomial. Okay, so if you fix j, for example, which is one interval, then the predictive function over that subinterval is the following. So here, Cj is just an indicator which is worth 1 if you fall in the proper interval, and then you sum over the the BLs times the predictor to the power L. Okay, so for example, Bj0 is the kind of level. Bj1 would be the first order coefficient for the polynomial. Bj2 would be the second order coefficient for the polynomial for subinterval j. Okay, so we see that having this summation for predictors entails that for each subinterval and for each order, not order, but each, how do you say that? So if you have a polynomial of order 2, you should have monomials of order 0, 1, and 2. So this is each subinterval and each monomial. You have the coefficient of that monomial times the associated power of the predictor. And having something like this entails that over each subinterval, that you have a predictive function of order d here. So that's great. This relaxes the assumption that you're constant in all subintervals, but it's not over yet. Okay, so as we saw in you have piecewise polynomial function of order d. So the order is the same for all the intervals, but the coefficients of the polynomial will vary over the different cutoffs interval. Okay, so maybe let's draw something. So here, let's say you have C1, I think, or was it C0? I think it was. Okay, does it start at C0 or C1? Let me just check back. Okay, it starts at C1. Okay, so let's go back here. Then if you draw the picture, you probably have something like C1, C2, C3, etc. Okay, so over each of these subintervals, this is x, and this is your prediction, then you'd have a polynomial. So let's say if we take d is equal to 2, maybe we have a parabola like this, and maybe then a parabola, and maybe here a parabola, and then maybe here a parabola, etc. Okay, so here we can see that we can have piecewise polynomials as a predictive function. So when we use this technique, question we ask is, what's the order d we should select? Well, because there are many, in practice, there are typically many subintervals for that, we'd like to have an order d which is not too large, because first, even with low order polynomials, you could still get a pretty good representation of many patterns. And if d was too large, then you'd get many parameters to estimate. And typically this would entail some overfitting. Okay, so typically when we use this approach, we would use d not too large. So for example, d is equal to 1, to 2, to 3, but we rarely go above that. Okay, so very common choices would be linear functions, so piecewise linear or piecewise cubic functions. So order 2 is used also, but we mainly hear about 1 and 3 in practice. Okay. But now what's the issue with that is once more, now we don't have constant values across all subintervals, but we still have discontinuities. Okay, so we see that the first parabola, there might be a gap with the second one, and etc. Whereas it might be desirable to have a predictive function which varies more smoothly and at least continuously with respect to the various values of x. So we like to maybe to prevent these kinds of gaps at each knot within the prediction function. Okay, so is there a way we can do that? And the answer is yes. So the solution to do that is simply to impose some constraint on parameters, so the coefficients of the various polynomials and the various subintervals, to ensure that the predictive function is at least continuous, and sometimes we add additional constraints to ensure that the predictive function has some degree of smoothness. Okay, so here we have to be a bit careful because smooth in mathematics has a very precise definition. So let's say it's infinitely differentiable or something like that. So here we will use the word smooth not as in a manner that is so precise, but more in a loose way. Okay, so smooth doesn't mean infinitely differentiable, but means something that varies not too abruptly. Okay, so smooth here we'll use it a bit loosely. It's not necessarily the typical mathematical definition of smoothness. Okay, so we like to have continuity and smoothness not only between the knots but at the knots also. So we can define piecewise polynomials which satisfy these constraints, and these are typically referred to as regression splines. So regression splines are piecewise polynomial predictive functions which meet some constraints related to continuity and smoothness. Okay, so first we'll discuss the continuity constraint. So how do we obtain continuity? Well, we must impose that for any knot Cj, so any endpoint of the interval Cj, the limit of the predictive function when we go from the left must be equal to the limit of the predictive function when x goes to Cj from the right. Okay, and recall that under our piecewise polynomial predictive function, the predictive function has the following form here. So here, this is the sum across all subintervals and all monomials of the related beta, so the coefficient times the monomial value. And here, this is simply an indicator to say in which subinterval you're falling, because there's only exactly one Cj that is equal to 1 at the time, and for a given value of x, all other Cj's are equal to 0. Okay, so if we want this constraint here, we must have that at the point Cj, coefficients from the left side, okay, so coefficients for x just smaller than Cj, which are the beta j minus 1, should entail that this function is equal to also the same value, but where x is greater than Cj, and the coefficients beta are the beta j's. Okay, so if you replace x by Cj here, this entails that this summation, okay, so here here on the left side, when x is smaller than Cj, it's only Cj minus 1 that is equal to 1, and all other indicators are 0. And where x is greater than Cj, then it's Cj which is equal to 0, and all the other C's, capital C's, are 0. All other indicators are 0. So if we see that, then having this and replacing x by the limit here, which is Cj, entails having this set of equations. Okay, so for all knots, so all j from 1 to capital K, where capital K is the total number of knots, this entails having this. Okay, so the sum of bj minus 1l j to the power l must be the same thing, but with coefficients on the right side. Okay, so how to look at that? Then if you have Cj, then on the left side, coefficients of the polynomial are b j minus 1 L, and on this side the coefficients of the polynomial are bj L, for L goes from 0 to d. This is an L. Okay, so this is the constraint we must have. So we have to choose the betas so that they meet this constraint. And this is equivalent to saying, so if we just isolate the first beta of this equation, this means that we simply have to set beta j0 is equal to beta j minus 1, 0 minus, so here what we do to get this, we simply take all terms from L goes from 1 to d, and all these terms we put them on the other side. So this entails that beta j0 is beta j minus 1, 0 minus the sum for all L's of beta j minus beta j minus 1 CJL. Okay, so this, we see that imposing this constraint leads to this, which entails simply constraining the beta j zeros. Okay, so the first order coefficients associated with the first order monomial for each subinterval. Okay, and this is for each j. So once you fix beta 0, 0, then this entails fixing beta 1, 0, beta 2, 0, beta 3, 0 until beta capital K 0. Okay, so all other parameters associated with higher order monomials can vary freely, but the parameters associated to the monomial of order 0 are constrained by this relationship. Okay, so this is to get continuity, and we can also continue on this to impose other constraints, such as the smoothness constraints we've discussed. Okay, so as we said, we don't necessarily want to have sudden changes in curvature for the prediction function. So maybe we don't want something like that, like a V, but we like more smooth variation. So in this case, we can add additional constraints to impose these conditions. Okay, so and what we're going to do next, we're going to consider the case d is equal to 3, which are known as cubic splines. And why we consider this case, it's because this case is very extensively used in practice. Okay, so cubic splines are very, very, very often used for function approximation in practice. So for cubic splines, what happens is we still impose, okay, so first it's you have piecewise cubic functions for the prediction. We still impose a continuity constraint we've discussed earlier, but now we also impose two other additional constraints, which are that the first and second order derivatives of the prediction function always exist. So they exist not only between nodes, but at nodes also, and moreover, they have to be continuous. Okay, so having continuous first and second derivatives ensures that you have some degree of smoothness. So the second order derivative relates to the convexity. So you cannot have, if you have that, you cannot have a function whose convexity varies abruptly at the node. You will have that the convexity varies smoothly, like continuously. Okay, so how to get these? Well, I'll just go back a few slides. So recall that the prediction function is still of this form, but now we must impose constraints that the first derivative and the second derivative exist and are continuous. Okay, so for the continuity, we had this constraint, but now what we have to do is, if we want to have continuous first derivatives, is to have this, and continuous second derivatives is have to add f prime prime. The limit of f prime prime on the left side must be equal to the limit of f prime prime on the right side. Okay, so to do that, well, to get f prime or f prime prime, it's pretty simple. So if you do f prime prime, f prime, for example, f prime would be of the same form. So this double summation of beta j l c j x. So this doesn't change. And what changes here is instead of having xl, it becomes x here. So the L goes in front, you get x to the power L minus 1. And here, instead of starting at 0, it starts at L equals to 1. Because the terms when L is equal to 0, this x becomes a constant. So when you differentiate with respect to x, the term disappears. Okay, so you obtain this. And here, if you want the second order derivative, you just take this expression and differentiate twice. So you still have this double summation here, but now the sum starts at 2 from 2 to d, and you still have beta jl cjx, and now the second derivative of x to the power L is L times L minus 1 times x to the power L minus 2. Okay, so basically these are first and second order derivatives. You can plug them into this equation, and if you do that, you get the constraints we're going to exhibit on the next slide. Okay, so for the first order derivative, the constraint becomes this. So, and now the summation starts at 1. So if we have this constraint, then what we can do is, once again, we can isolate the first term of the the right-hand side. So the first order term here is beta j1, and we have that this guy is equal to beta j minus 1, 1. So the first term here minus the summation so if we take all terms on the right side starting at L is equal to 2, we throw them on the other side, then we get this new summation. Okay, so we can see that imposing a continuous first derivative on the piecewise polynomial is equivalent to constraining the first order betas of the function. Okay, so if you know beta 0, 1, then from that relationship here, you know beta 1, 1, and then from beta 1, 1, you know beta 2, 1, and from beta 2, 1, you know beta 3, 1, etc. Okay, so this constrains all betas of the associated with first order monomials. Same thing here, we can repeat that step for to impose that the second order derivative is continuous. Okay, so here the summation start at L is equal to 2. So what you can do here is you can take the first term here and isolate it. So this becomes twice beta j2 is equals to twice beta j minus 1, 2. And then throw all other terms of this summation on the right side, and then you get this summation. So now we see that this constrains the second order coefficients beta for our piecewise polynomial. Okay, so we can see that if we do that, the only free parameters that can vary freely are the betas when j is equal to 0, so the first betas associated to the first subintervals, and when we set them, the only other parameters that can vary freely are the beta j3, okay, because the beta j0s are fixed by the continuity assumption. The beta j1s are fixed by the continuous first order derivative constraint, and the beta j2s are constrained by the second order derivative constraint. Okay, so the only thing that's left to vary freely are the beta j3s, which characterize the third order variation. Okay, so now we've seen how to get these properties, so to impose either continuity or some degree of smoothness to piecewise polynomials. So we'll illustrate these methods through an example from the Introduction to Statistical Learning textbook, where the following four models were fitted. Okay, so the four models that were fitted is first a piecewise cubic polynomial. Okay, so here this means that it's only cubic, but there's no constraint imposed on either continuity or smoothness at the nodes. You have continuous piecewise cubic model. Okay, so here we impose continuity at the nodes, but we don't impose smoothness through continuity of derivatives. There are cubic splines, which are the most smooth version, where we impose both continuity and continuous first two derivatives even at the nodes. And finally, there's the linear splines, where we have a continuous linear function. Okay, and for simply for illustrative purposes, a single knot was used. Okay, in practice, you use many knots when you do that kind of thing, but just for the example, a single knot was used to illustrate what's happening. So we see here for the piecewise cubic, we have a discontinuity here, and the convexity varies somewhat suddenly here. So this is not necessarily a good predictive function, because you'd expect that right before age 50 and right after. So, okay, this example from the textbook entail comparing the wage of people with respect to their age. Okay, so you could expect in practice that your wage right before 50 years old should not be very different from your wage right after 50 years old. Okay, so it's not very logical to have that kind of big gap here, but if you only use piecewise polynomials without imposing continuity, then you would get prediction functions like this, which is not super appropriate. Now the second example is the continuous piecewise cubic function, where continuity was imposed, but we did not impose continuity of first and second order derivatives. And we can see here that it's like a small m here, where the convexity of the function and the slope, they vary I'd say somewhat abruptly, so not continuously, but there's kind of a little hump. We don't see it here a lot very clearly because it's a bit small, so we might need to zoom. But at there's something like this. It goes down and just up again. Okay, so we see that the slope varies not smoothly, and this again might be considered weird because there's no reason why at this precise point 50 the slope would change abruptly, but for all other ages where there's no knots, then you don't have these kind of unsmooth variation. The third example is the cubic spline, where continuity was imposed and the first two derivatives had to be continuous, and then we see that we have much smoother behavior, so this would make more sense as a predictive function. And then finally we have a linear spline, where we have piecewise linear function. So once again we see that at the knot the slope varies abruptly. So here before running any prediction, there's no reason why the age 50 should be an age where the slope changes abruptly, but for all other ages you don't have these kind of changes. Okay, so there's nothing in particular that happens exactly at 50 years old. So if you use this kind of model, again, probably might not be appropriate. So this justifies why we use first piecewise polynomials instead of piecewise constant functions for prediction, and why we add these additional constraints to ensure continuity at the knots and continuity of some of the derivatives. So the cubic spline is probably the most famous example encountered in practice, so it's important to understand this one. Okay. So as we just said, if we fail to impose either continuity or smoothness constraints, the prediction functions can look somewhat erratic, and this might not be appropriate for predictions. Okay, so the cubic spline is the more consistent with the expected behavior of many phenomena, which vary somewhat smoothly in terms of the predictor. Okay, so now uh, the question that that emerges from this is how can we fit a cubic spline? So let's say we can have we have a cubic spline function that we want to fit, but we like to determine coefficients beta for a given data set using linear regression. So one thing that you could do is try to solve the constraint optimization problem directly. So you try to select the betas which minimize the mean square error of prediction and do a constraint optimization with all the constraints seen before. But there were many constraints earlier, so this can become a bit inconvenient if you do that directly. So what we're going to see here is how to directly obtain the solution. Okay, so it turns out that the solution from the previous constraint optimization has a pretty nice form. So in practice, it's more convenient to use this nicer form than to try to solve directly this this problem we exhibited earlier. Okay, so let's assume we want to fit a cubic spline with capital K naughts denoted by C1 until Ck. And let's define the following function. So h of x and xi is defined as x minus xi plus to the power 3. Okay, so plus means 0 if x is smaller than xi, or x minus xi if x is greater or equal to xi. Okay, so if x is equal to xi, this is 0 anyway, so it doesn't matter. But so this term, if x is smaller than xi, then this term is 0. If x is greater than xi, then the whole thing would be the cubic term x minus xi to the power 3. Okay, so if you plot that kind of function, this is x, this is a given value here of xi. So if you plot that, that function is basically something like this. It's 0 until xi, and then here this is a third degree, like canonical third degree polynomial. Okay. So this function h will be needed to describe the solution to the cubic spline problem. So here let's define the following. bjx will be defined as h of x times cj minus 3. Okay, so for a given j, this entails using the knot cj minus 3 to characterize the function h. So this acts as the psi we exhibited in the previous slide. So it turns out that for a cubic spline function, we can express the predictive function as this. Okay, so it turns out that the solution to the previous cubic spline, which is to optimize all these betas under the constraints, well, it turns out that the cubic spline has the following representation, which is much nicer and which can be directly used in a linear regression model to fit the betas. Okay, so it turns out that if you define a function x, f of x, which is the following, so this is a sum from j is equal to 0 of beta j xj, so this is a regular third degree polynomial across all possible values of x. And if you add the following summation, so you sum from j goes to 4 until k plus 3, beta j bjx. Okay, so here, this function bjx, if you look like this, this is cj minus 3. So bjx varies like this. Okay, so this is cj minus 3, this is bjx. So we can see that bjx just add a third degree, third order polynomial to the right of the knot cj minus 3. Okay, so if you define the following function like this, it turns out that this function is a piecewise cubic polynomial with a continuous second derivative. Okay, so the only possible derivative that can be discontinuous at the knots is the third order derivative. But for derivatives of order 1 and 2, you have continuous derivatives. So now we stated the result. It remains to prove that statement, and the proof can be found in the exercises. Okay, so please go through the exercises and do the related exercise to understand this result. Okay, but this result is very fortunate because why is that the case? It's because the function f, the cubic spline, can be expressed as a linear combination of predictors, where the predictors of the first four predictors are powers from order 0 to order 3 of the original predictor x, and the predictors for predictors 5, 6, 7 until k plus 3, these can be computed easily using this function h here. So you can bj of x for a given value of x. It's pretty simple to compute. You just plug x in here, and here recall that this is simply equal to x minus cj minus 3 plus to the power 3. Okay, so if you plug x like this is just you take the minimum between that quantity and 0, you put to the power 3. So this is extremely simple to compute in practice. So all these predictors, the xj's and the bj's x, are very easy to compute for a given value of x. So we can see that this is indeed a linear model, and it means that a cubic spline can be obtained through linear regression. Okay, so the cubic spline has exactly k naughts and turns out to have exactly k plus 1 free parameters to be estimated. So why is that the case? Well, we said that for a cubic splines, the parameters that vary freely are first the 4 betas associated with the first interval, and then for all other subintervals, it's the beta associated with the third order monomial. Okay, so you end up having 4 parameters for the first interval, and then for the remaining k subintervals, you have exactly one parameter which varies freely, which is beta associated to x to the power 3. So in total, you have k plus 4 parameters to be estimated. Okay, so as we mentioned, the previous shape of the cubic spline works very well for as a linear model. It can be expressed as a linear model. So you can use this following linear regression to estimate parameters of the cubic spline. So here the response for the ith observation, it's the sum of beta j xi to the power j. So here this is simple to compute, and here you have all the bj's we defined earlier. So this is indeed a linear model that where the betas here can be applied, obtained through linear regression, and the x to the power j's and the bj's, all of these can be obtained from the original predictor xi, and by once you've determined or once you've decided the knots c1, c2 until c capital K. Okay, so fitting this in practice, there's no real technical difficulties to this. Okay, so this is great. Cubic splines work well for many problems, and it's often used in practice. Now we're going to discuss a slight refinement associated with cubic splines, which are natural splines. So the issues is that the variation of cubic splines is very smooth for non-extreme values of x, but if you're at the outer range, so the first subinterval minus infinity to c1 and the last subinterval c capital K to infinity, on these subintervals the spline predictions associated to spline tend to vary a bit wildly. Okay, so the reason all the splines for subintervals in the middle, they're kind of tied to the polynomials on intervals right next to them. But if you're at the extremity, you don't have any other polynomial to be attached to, so these last polynomials can vary a bit wildly at the end. Okay, so if you calculate the confidence or prediction confidence intervals at the outer range, so for the last subintervals, then of values of x, they tend to be very large because of that. For the last subintervals, for values of x within the last subintervals, predictions tend to vary a bit wildly. So the solution to this is to impose an additional constraint on the polynomials for the first subinterval and the last subinterval. And this, to do this is to reduce the variance of predictions for these two extreme. So for values of x falling into these two extreme subintervals. Okay, so a natural spline is a regression spline, which we've discussed earlier, with additional boundaries on the constraint. So the typical way to do that is to impose that you have a piecewise cubic function. So for all subintervals, the polynomial is cubic, but for the very first one and the very last one, you impose additional constraint to force them to be linear. So basically, these natural splines, an example is to have a piecewise polynomial where you have linear, cubic, 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 and then for the last one, linear again. Okay, so this entails that your spline is more stable at the two endpoints here, or the two last subintervals, and you have more predictions for the extreme values of x. So here, once again, I've picked this figure from the ISL textbook where they illustrate the fitting of a natural cubic spline where you impose linearity on the first and the last subintervals here versus the cubic spline, regular cubic spline, which does not impose these kind of constraints. So we see that, and they use 3 knots. So first knot, second knot here, and third knot here. So we see that for the values in the middle, the predictions are not heavily impacted by this additional constraint for the first and last subinterval. So the prediction curves for the red curve is the natural cubic spline, the blue curve is the regular cubic spline. So predictions are pretty much overlapping, and confidence intervals are also the same. But now if you go to the two extreme subintervals, on the right side, the predictions are pretty much overlapping, but on the left side, you can see that there's some form of departure. So the blue curve here is a cubic function, whereas the red curve here is a linear function. So we can see that this entails that the predictions depart at the endpoint, and the prediction varies more wildly for the blue curve than for the red curve. But what we see also, it's not only the prediction intervals, the predictions themselves that are more stable, but if you calculate the confidence intervals for these predictions, they are wider for the blue curve, and thinner for the red curve. Here, this is very apparent, like obvious. So you can see that the red prediction interval is more tight. So the imposing linearity on the first and last subintervals generates more stability in predictions and tighter prediction intervals, which can be desirable. So you reduce the variance of predictions on the outer range of x, and for that reason, smaller variance is associated to smaller MSE of predictions for new observation if you don't increase the bias. Okay, so reducing the variance of predictions is very important, as we've seen in chapter 1. So if you can do that without imposing too much additional bias, this can be a good way to proceed. Okay, so this natural spline, we won't go into details on how to fit this, but I wanted to let you know that this technique exists, is a nice generalization of cubic splines, and which can solve one well-known problems of cubic splines, which is the erratic behavior on the first subinterval and the very last subinterval beyond the last knot. Okay, so now one last topic we will discuss is smoothing splines. Okay, so what happens in the regular splines case? If the number of knots is sufficiently large, then the cubic spline will pass exactly on every data point. Okay, so let's say you have n data points and you have, I think it's n minus 3 or n minus 4 knots. Yes, because you have k plus 4 parameters. So I think it's n minus 4 knots. Then you can have a polynomial which passes, if you select the knot suitably and you have one data point per subinterval, you can have a spline which passes exactly through all the data points. Okay, so you can always, if you use enough knots and you place them suitably, you can always have a null training MSE. So pass exactly through all points, and then in this case, the splines is not used as a smoothing method, but rather as an interpolation method. Okay, so you find a curve which passes through exactly all the points, and you can use this curve to interpolate between 2 points to find the suitable value. Okay, so this approach, if you have many knots, you can think of them as interpolation splines. Okay, so you pass within all points and you interpolate with that to make new predictions. So if you apply that to to data where there's a lot of information of observations, this will systematically lead to overfitting. Okay, because if you have, let's say, data points that are like this with a lot of noise, then the splines will go like this to pass through all points, and this will generate systematic overfitting. Okay, so the splines curve would be very bumpy. Okay, so one way to prevent this is to, of course, use less knots. But if you use less knots, then you have less possible adjustments for the curvature or the of the splines. Okay, so sometimes you want to remove that overfitting, so you'd say, well, I'll use less knots, but less knots gives less possibility for adjustments of the curvature, because the curvature is only modified every time you have a knot. Okay, so the convexity, no, but the third order variation varies at the various knots. So if you want to prevent that, so you'd still want a lot of flexibility to change the curvature for many values of x, but you don't want to have overfitting, then another alternative is called the smoothing splines. Okay, so we're going to see another technique based on splines to handle this problem. So if we go back to the splines we've defined earlier, which were for example, the interpolation splines, or the splines we've defined through the ordinary linear model earlier, then if you want to fit the betas, typically what you do is you minimize in sample or training mean square error of observations. Okay, so when you have a splines to fit, you want to find the beta, then the problem was to find the splines function, g, which minimized the squared prediction error, the sum of squared prediction error, so the sum of responses in your data set minus so g is the spline function we've outlined earlier, so we called it f, but now let's call it g. So here yi, the response, minus the predictive value for the ith predictor, not the ith predictor, but the predictor for the ith observation squared. Okay, and here g, as we said, is the predictive function associated with our spline. Okay, so if we fit the regular splines seen earlier through ordinary least squares, this simply entails minimizing the training errors. So as we said earlier, if there are many knots, then the curve will be extremely bumpy to really try to pass through all points, or maybe as close to all points as possible. So it's pure in sample error minimizing. Okay, so this will tend to lead to overfitting. So to avoid this kind of overfittings, we like maybe to impose some conditions on the smoothness. Okay, so we've already, in splines, there's already constraints on the smoothness, which is continuous. In cubic splines, for example, continuous first and second order derivatives. But maybe we need additional constraints or penalty on absence of smoothness, so as to not get an erratic behavior like this and have more slowly varying prediction. So instead, it's possible to use what we call smoothing splines, where we use another objective function to be minimized when we form the predictions. Okay, so the idea here is instead we could try to find g, some predictive function. Okay, so here we right now we okay. So right now, let's assume that we don't restrain ourselves to cubic splines. We consider general prediction functions, but we'd like to find a general prediction function g, which solves the following problem. Okay, so we'd like to find a function g, any function g, not necessarily a cubic spline, which minimizes across all functions g the sum of squared prediction errors in our training set, plus here this penalty term, which is plus lambda, some constant, which will represent the intensity of the penalty, times the integral over t. So t is all the possible values of the predictor, so you can think of t as x instead, so it's the predictor. And what you have inside the integral is the second derivative squared. Okay, so and here lambda will be a constant greater than 0. Okay, so this second derivative squared, why do we impose that? It's because if the second derivative is 0, then the function is linear. Okay, so there's no abrupt variation like this. Conversely, if you have a function like this, the second derivative will often be very positive or negative, because the convexity has to change very often to yield this kind of behavior. So we can see that if the function varies very slowly, this quantity should be small. If the function is very abrupt like this, then this quantity should be large. Okay, so we can penalize the non-smoothness by imposing this kind of penalty in the objective function. So if we want to find some predictive function g, so as solving this problem, we are trying to find a suitable trade-off between accuracy of predictions and again, I want to say smoothness is smoothness in the loose way, in the sense that you don't have very erratic curves like this, but you have a more slowly varying curve. Okay, and here in this original problem, we don't impose piecewise cubic function. We just impose that we find any predictive function within the set G, where the set G is the set of all twice differentiable functions. Okay, so we don't say anything about the shape of the function more than it being twice differentiable. Okay, so as we just said, here the absolute value of the second derivative will be large, typically large if the curve is very bumpy like this, or it will tend to be small if the curve is not bumpy at all. Okay, so as we said, this second term here is a penalty which tries to reduce the bumpiness of the prediction function, where the prediction function is a mapping between the value of the predictor x and the predicted value of the response. Okay, so this entails, as we said, finding some optimal trade-off between minimizing training errors, so accuracy in sample, and minimizing the bumpiness, or like non-smoothness used in a loose way associated with the prediction function. Okay, so now if we go back here, there's this constant lambda that determines the intensity of the penalization. Okay, so in practice, how do we find lambda? Well, it's the same thing than for other uh, like penalization methods we've seen earlier in chapter 3. So typically to find the suitable lambda, it's through cross-validation or like out-of-sample performance assessment. Okay, so here lambda determines how much you will penalize bumpiness and how much you're ready to impose additional bias and remove variance. So to find this suitable bias variance trade-off, it's once again through out-of-sample performance assessment that you can do that suitably. Okay, so you don't know in advance. Lambda typically has to be calibrated to minimize out-of-sample errors. Okay, but what are limiting cases? So as lambda shrinks to 0, then the penalty term completely vanishes. So let's go back to slides. If lambda is 0, this term vanishes, and the objective function simply becomes minimizing the square prediction errors in your training set. Okay, so this entails going back to regular OLS approach, which is only meant to maximize accuracy in your training sample, and this might lead to overfitting. Okay, but here the limiting case when lambda is 0 is just minimizing in sample accuracy. Okay, so the function g, it can become very bumpy to try to pass as close as possible to all points and try to interpolate between all points instead of smoothing the prediction curve. Conversely, as lambda goes to infinity, so if we go back here, if lambda is very, very, very large, then the first term, accuracy term, becomes negligible with respect to this one. So the prediction function only tries to reduce the second order derivative. And the way to do that is to obtain a prediction function that is a straight line. Okay, so if you have a straight line as the prediction function, then the second order derivative is 0 for a straight line. So this term is equal to 0. Okay, so when lambda becomes very large, the problem is almost only to minimize the convexity, and this is done by having a straight line predictor. So as lambda goes to infinity, this simply becomes a linear regression, okay, where you converge to the optimal solution being a straight line. So this would entails having an OLS problem where you have a linear regression. So you don't have within your set of all twice differentiable function, you would only entail having a straight line as a solution. So in practice, often the solution might be not to have lambda too small, so to penalize bumpiness, but not having lambda too large to still get an amount of flexibility, not to have a straight line, but to have some amount of curvature. So to find the suitable lambda, as we said, this is typically done out of sample. Okay, so now we said we have to pick G among a set of twice differentiable prediction function. So this set of function looks pretty large, so it's probably a very hard problem to solve. But some people have shown that the solution to this problem is of the following form. It can be shown that to solve this problem, the solution G is a cubic spline where the knots are x1 until xn. Okay, so if you want to find the most suitable G, you can restrict your search through all cubic splines which have knots x1 until xn, which are the predictors for all data points. And recall here we give the example for the univariate case. We assume that there's a single predictor for each observation. Okay, this can be generalized to multivariate predictors, but just for simplicity, for the sake of explanations, we do the case with a single predictor. Okay, so it can be shown, we won't show this here, but it can be shown that the solution to this problem where we search across all twice differentiable prediction function is a cubic spline. But a quick remark here, this spline does not coincide in general with the OLS regression spline on the same knots. Okay, so if we considered all cubic splines on these knots, we could find the non-smoothing spline, so the spline with lambda is equal to 0 with these knots to minimize the training MSE. And this cubic spline for lambda is equal to 0 will not coincide with the optimal cubic spline on these knots for lambda different than 0. Okay, so both the solution to both lambda is equal to 0 and lambda different than 0, both are cubic splines on these knots here. Sorry. If you use lambda and 0 in these knots, you get a cubic splines. And if you use lambda different than 0, but with any knots, you still get a cubic splines with these same knots. But the both splines will not coincide together. Okay, so as we said, the reason is that this lambda constant adds or drives the penalty here, and that penalty changes the optimal spline. Okay, so the optimal spline might be much bumpier than the optimal smoothing spline, which has to kind of address this penalty here. Okay, so now let's go back one slide here. We see that this is the objective function we're trying to minimize when we fit a smoothing spline, and we see that this objective function doesn't depend anymore exclusively on training errors, but there's an additional penalty term here, which is a bit harder to express. So because of that, smoothing splines, they cannot be estimated with linear regression directly. Okay, so we saw earlier that cubic splines, you can fit them through linear regression, but smoothing splines, it's not as simple. So the formal procedure to optimize a smoothing spline, it's left out of scope. It's a bit more complicated, so we shall not discuss that here. But if you want to apply this method, you can use R, and there's the function smooth spline in R that can do this, and probably there are many other packages and other programming languages that can do the same thing. Okay, so here we have provided the general idea about smoothing splines, where you find some suitable trade-off between accuracy in sample and bumpiness, but we will leave details aside on how to fit them, but this can be done through existing packages in R, for instance, or in other languages. So we'll stop here for this lecture, and I'll see you next time for the last video of chapter 4.